Hi students, I am Dr. N. Manimegalai. Today I am going to teach you about a most promising area of food packaging technology, that is non-migratory bioactive polymers. As understood from the term non-migratory and bioactive, non-migratory bioactive packaging is made up of polymers that exhibits biological activity such as antibacterial or antimicrobial, etc. They won't affect the active component which is migrating from the polymer to the substrate, that is your food. Bioactivity is expected due to immobilizing bioactive molecules such as enzymes, peptides, proteins and other organic compounds into the synthetic polymers, or it may be result from an inherent bioactive capacity of the polymer itself. Best example for this category is Cytogen. Coming to the merit of this technology, we can classify the merit of this technology in three aspects. Number one is technical aspect, number two regulatory aspect, and number three marketing aspect. If you look at the technical aspects, we can discuss the technical aspects in terms of its challenge. It means the challenge lies for two things. That is, first one is the challenge in bringing the improved stability of the bioactive substance, and number two challenge is concentration of the bioactive effect at a specific locus. Improved stability of bioactive substance helps in adopting this technology to a broader range of food products. Further, improved stability means improving the thermal stability of the bioactive compounds without affecting the degradation due to its processing conditions such as temperature, pH, etc. For example, polymers are often processed at a very high temperature that would denature the native proteins, thereby which leads to the loss of its activity. By means of improved stability of bioactive substances, we can achieve this through polymer conjugation. This technique is commonly adopted to improve the stability of the immobilized bioactive substances against the environmental conditions. So, what are those environmental conditions? They are, it may be a high or low temperature, or it may be a pH, or it may be a pressure, high shear, ionizing radiation, presence of high electrolyte concentration, and chemical media like organic solvents, or it may be a supercritical fluid and gases. So, coming to the second challenge of the technical aspect is maintaining the desired concentration of bioactive substance in a specific location within the package. For example, more amount of antimicrobials on the surface of the packaging used for many minimally processed food products. So, food products includes a fresh meat, or it may be a fresh cut fruit or vegetable, or it may be anything else. So, which allows the minimal amount of the active components to be used to maximize the effect, since the majority of the microbial spoilage occurs on the product surface. Similarly, another known example for this claim is placing the enzymatic spoilage indicator in the food package headspace. Headspace is usually the space which is located above the food product. So, if you look at this, most of the spoilage occurs on the headspace. Okay. So, the substance will present on the headspace so that you can avoid the spoilage of microbial growth and the high concentration. The finding solution for these technical challenges not only helps in effective use of expensive materials such as enzymes, it also reduces the possible undesirable reactions between the food and the active molecules. The second aspect, that is nothing but your regulatory aspects. Coming to this aspect, that is the regulatory aspect, the regulations relating to the active food packaging are still evolving. There are currently no specific regulations in India. Instead, these packaging materials are subject to same regulations as that of the traditional packaging. So, what are those regulations? They are: all packaging materials of plastic origin shall pass the prescribed overall migration and color migration limits. Number 2 regulation is the packaging must not affect the composition of the packaged food which is inside the packaging material. While active and intelligent packaging is not subject to any special regulatory concern in the United States, the regulation of such packaging material in Europe is still evolving. Since December 2004, a new European Union framework regulation on food contact material is in effect. The new framework regulation sets forth the definition for what is active and intelligent packaging material, and it also emphasizes certain requirements for the use of these materials in the European Union. Suppliers of active and intelligent packaging materials on the European market needs to make sure that their materials comply with the General European Framework referring to the regulation number EC 1935-2004, Articles 3, 4 and 15, as well as EC 450-2009. Further, regulation number, that is EC 450-2009, lay down specific rules for active and intelligent materials, and also the articles intended to come into contact with your food material. These regulations are published in the official journal on 29 May 2009 and become active on 18th June 2009. Further, the regulation number, that is EC 450-2009, sets out the composition restrictions, the requirements concerning labeling and declaration of the compliance, which is nothing but supporting documents from the suppliers dealing with all kind of things like active intelligent materials and articles intended to come into contact with the food. Composition restrictions include the use of substances which are included in the community list of the authorized substances that may be used in components of active and intelligent materials as well as the articles. The regulations also direct to use "do not eat" label with relevant symbol wherever non-edible part are included in the packaging material. In addition to this, regulation number, that is EC 450-2009, also sets out in all marketing stages active and intelligent materials and articles, whether they are in contact with food or the components intended for manufacturing those materials or substances for the manufacturing of those components, all shall accompany with a written declaration in accordance with the regulation number EC, that is 1935-2004 and EC number 450-2009. So, coming to the third aspect, that is the marketing aspect of the non-migratory bioactive polymers. Today, if you look at the consumers are very much quality and health conscious. They demand a safe and quality products. In case of production of lactose-free milk, the lactase enzyme cannot be added to the milk because of the heat liability of the lactase enzyme. That means the lactase enzyme will die if you add during the processing or during the milk pasteurization process. This can be very well done during the post pasteurization. That means after pasteurizing the milk, you add the lactase enzyme so that the lactose will be degraded and the product will be consumable without any lactose. But this can be achieved after a brief storage of milk under proper storage condition. So, coming to the disadvantages. What are the disadvantages? Any innovation, if you look at, it has its own limitations. NMBP technology has no exception from this statement. Some of the limitations of the technology, if you look at it, number one limitation is the minimum zone of activity. That is, for a given concentration of bioactive substance, the area experiencing inhibition of spoilage remains less. This limitation actually prevents the application of this technology to a viscous and solid product, because they cannot, the viscous and solid products cannot be mixed properly. One way of minimizing this limitation is ensuring proper contact of the food product with the packaging material. So, coming to the second limitation, it requires a specific environmental condition for the effective activity of the active agent, because the active agents are nothing but the biological agent, they are the living entities. So, we need to give them a proper environment to act, to work for the specific task assigned to them. It includes, what are the environmental conditions? Those are the optimum pH and optimum temperature. So, coming to the third major limitation, it is the loss of activity of the active agent. Reduced or complete loss of activity of immobilized bioactive compound is found to be a major limitation of NMBP. So, understanding the mechanism behind how the activity, how the bioactive agent works is very, very important to reap the maximum benefit out of this new technology. The place at which the covalent linking exists with the polymer. And the next is the mechanism of action between the active agent and the environment in which the active agent is present. And the fourth one is some of the other important points, such as the state of bioactive agent, where the active site lies, and what is the requirement of the coenzyme for its effective activity. So, these all points are to be kept in mind to enhance the activity of the bioactive compound immobilized in the packaging material. However, the loss of activity may be reduced or it may be controlled through a proper coupling methodology, and in addition to that, maintaining the optimum environmental conditions. So, what is coupling methodology then? The detail about this methodology we will discuss bit later on this lecture. On contrary to the activity loss, there is no doubt that the immobilized active compound showed better stability under extreme conditions such as high temperature and inappropriate pH, etc., than the native form, that is the Cytogen or the inherent bioactive polymers. The other limitations include technology availability and the cost of the packaging material. So, commercial availability of this technology to produce NMBP is found to be yet another limitation. Unless the commercially available basic polymer surface functionalization technology control functionalization of inner polymer backbone such as polyethylene to create enough functional group for immobilization of active agent is still under research, which necessitates a wait to practice NMBP technology in a commercial way. Coming to the fifth limitation, that is the high cost of NMBP, could be very well related to the following things, that is nothing but your cost of immobilization technique, or it may be the additional processing step involved in bioactive polymers such as surface functionalization and modification, the cost of bioactive agent itself, and also the, of course, the cost of chemical used for the coupling process. Like any other new technology, when they are introduced in the market, it is expected that the cost should come down due to increased demand and reduced fixed cost. Thus, you can expect in a period of time. So, that will also applicable for this new technology. Coming to the first category, that is the structural polymers with modified backbone, for example, synthetic UV irradiated nylon, and naturally bioactive materials such as Cytogen. All the examples of inherently bioactive polymers to date involve antimicrobial activity. So, antimicrobial activity of this UV irradiated nylon is possible by several ways. You can modify the surface by physiochemical method by using a desired frequency UV waves. The UV treatment converts the amides on the nylon surface. The amides are present on the nylon surface. The UV treatment actually convert the amides on the nylon surface to amides, which remain part of the polymer chain and found to have responsible for the antimicrobial activity. The wavelength of this UV waves, the test media composition and the temperature, these are all the affecting factors. They found to have a influence on the antimicrobial activity of the UV treated nylon polymer. Further, it is claimed that the antimicrobial activity of UV treated nylon may be due to microbial membrane disruption or the adsorption of bacteria on the film surface. So, next type of material in this polymer are natural polymers. As you know, the natural polymer, the best example is Cytogen. So, this is the most studied, the Cytogen is the most studied inherently bioactive compound, that is bioactive non-migratory bioactive polymers. Though the Cytogen is declared as grass, that is nothing but the grass is nothing but generally recognized as safe. The high solubility of Cytogen in aqueous system is an issue, as it results in migration. The Cytogen is migrated into an aqueous product, which would include many foods, violating the non-migratory principle, because the non-migratory bioactive polymers, the migration should not be there. So, the migration, if it is there, it is violating the principle, non-migratory principle. However, most of the research and antimicrobial activity of Cytogen has been conducted in solutions. So, this is the one aspect, that is most of the anti-migratory research are conducted in solution, but it is not conducted with Cytogen films. So, fortunately the packaging material is nothing but film. So, this definitely demands the attention of the packaging scientist to this natural polymer as a potential non-migratory packaging material. So, coming to the third type, it includes a less popular inherently bioactive synthetic polymer, that is your hydrons. They are also termed as, you see, the hydrons can also be called as regenerable antimicrobial polymers. So, example of this category you can see here, the example are three type of examples are there. One is the polyethylene glycol, that is commonly usually called as PEG, or it may be a poly-L-lysine or a polylactic acid. So, coming to the second category of polymer, that is the polymers containing immobilized bioactive compound. The bioactive compound is immobilized in the polymer, or this is the next step, next most researched category in the NMBP technology. Bioactive agent, it may be a peptide, as I already told, it may be a peptide, or it may be a protein, or it may be an enzyme. So, these compounds may be synthesized. See, you can synthesize the compound, or and the synthesization may be on the surface, or it can be synthesized externally, that is, it can be synthesized in a laboratory, extracted separately, and then you can covalently link the polymer. The polymer and the antimicrobial compound, active compound, may be covalently linked. So, this is the functionalization and coupling. For example, in case of immobilized packaging material, the functionalization and coupling chemistry are the two important mechanisms that is related to the immobilization of your enzymes. While functionalization, there are there is a slight difference in the definition of functionalization and the coupling technique. So, functionalization refers to a process in which maximum number of target functional groups are created on the inert backbone. So, polymers have a backbone, inert backbone. So, in that you have to create maximum number of functionalized group. So, the coupling chemistry, or otherwise the coupling chemistry is nothing but targeting the maximum available function. So, through functionalization you are creating the functional group, through coupling chemistry you are targeting the created functional group towards the attachment of the active compound. So, this is the these are the two important, that is the functionalization and coupling chemistry is the two important mechanism in case of immobilized bioactive polymers. So, functionalization at a laboratory scale is possible by several methods. So, one is the wet chemical oxidation of polymer surface using chromium dioxide, or potassium hypochlorite or potassium permanganate. In this treatment, you are creating various carbonyl functional groups such as carboxylic acid, aldehydes and ketones. So, these can be created on the polymer surface. Coming to the physical method of functionalization, it includes flame treatment and corona discharge. Corona discharge is nothing but applying a high voltage, that is around 10 to 40 kV light at a high frequency, that is around 1 to 4 kilohertz, between a discharge electrode and a earthen roller carrying the film. It oxidizes the surface of the film and it introduces a range of oxygen and nitrogen functional group to the polymer backbone. As I already told, polymer backbone is an inert material. Through this treatment, you are creating the various functional group. So, flame treatment is also produces an antioxidant film, that is similar like your corona. There is another treatment, that is flame treatment, that also produces oxidized film surface and introduces a range of oxygen and nitrogen functions, but is more difficult. The main disadvantage in this is difficult to control than the corona treatment. That means the functionalized group can be controlled very well in your flame treatment, but in corona treatment it is very little bit difficult. So, both the treatment requires specialized equipment. So, it may be a flame treatment or corona treatment. You need to have a specialized equipment for creating the functional groups. The limitation of both this method is to control the exact nature of the functional group created on the polymer surface. So, plasma treatment technology or possibly controlled atmosphere corona discharge treatment are likely to be the most useful commercial technique. In contrary to the above technique, whatever we discussed, that is your flame treatment or it may be a corona treatment, the plasma treatment is a commercially acceptable technique for creating a controlled surface functionalization of a broad range of polymers. Although the use of inherently biofunctional polymers, example polylactic acid, polyacrylic acid or polymethylacrylate or its derivatives, it may be more feasible. Polymeric spaces such as polyethylene glycol, PEG oligomers are generally used between the bioactive compound and the polymer backbone in developing the polymers with covalently immobilized. You need to have a polymer spacer. So, this PEG can be used as a polymer space to link the bioactive compound and the backbone, polymer backbone. Okay. So, coming to the these spaces basically reduces the, what is the use of these spaces? These spaces basically reduce the solvent denaturization and steric hindrance to efficient activity of the active compound. They also found to increase the mobility of the bioactive compound. So, they increase the mobility of the bioactive compound, thereby the efficiency increases. In the second category of NMBP, while functionalization was found to be important for creating sufficient quantity if functional groups in the inner polymer backbone, proper coupling chemistry needs to be chosen to target the available functional group. There are many coupling chemistries available for covalently linking the bioactive compounds to polymers to form different forms of linkages such as amide bond, which is basically created between an amino group and a carboxyl group, or it may be through a ester bond. It is generally created between the carboxylic acid and alcohol, or it may be a thioester bond which is created between the carboxylic acid and the diols. So, coming to the mechanism. So, what is the mechanism involved in coupling chemistry? This is similar to the one used in the peptide synthesis. How you are synthesizing the peptide, same technology, same mechanism is used for this also. The well developed coupling technique uses three types of reagents such as carbonamide or glutaraldehyde and succinimidyl succinate active esters and their derivatives. Succinimidyl succinate active esters and their derivatives are commercially available, and this is the extensively employed for PEG conjugation to peptides and the proteins. So, coming to the third type of NMBP category, which includes the polymers containing enwrapped bioactive compounds. So, this category of polymers are made by enwrapping the larger size active compounds into the channel present in the molecular structure, unless the immobilized technique in which you are actually linking the bioactive compound to a polymer backbone, whereas here in the polymer itself you are inserting the bioactive compounds. So, in the polymer, inside the polymer you have a channel. So, inside you are enwrapping the bioactive compounds. Application of NMBP. Coming to the application of NMBP in food packaging, some of the food packaging related to application of NMBP includes in-package processing, antimicrobial packaging or shelf-life extension, and intelligent packaging. The basic principles of this in-package processing is that the immobilized enzyme conduct the packaging food products due to natural convective currents or diffusion within the product or due to mixing caused by the product agitation during handling and distribution, thus producing the desired effect. The reaction products are basically released into the food system itself. The desired effect is achieved due to sufficient storage. So, you have to give sufficient storage. Coming to the second category, that is antimicrobial packaging. Shelf-life extension and reduction of foodborne diseases are the two main goals of antimicrobial packaging. While prevention of pathogen growth and inactivation of those present in the food is the principle behind the prevention of foodborne illness, the growth rate reduction, lag phase extension and reduction of limiting reactions such as oxidation by removing catalyst or reactants are the main principle behind the shelf-life extension packaging material. Several synthetic and natural compounds were researched to produce non-migratory antimicrobial packaging. For synthetic compound, best example is CTA lysozyme film. CTA film is nothing but cellulose triacetate. The film was manufactured by immobilizing lysozyme derived from hen egg white in cellulose triacetate. However, the activity of the CTA lysozyme film decreased with repeated usage. This may be due to the reduction of lysozyme activity or migration of the active compound. So, example for natural antimicrobial system includes the activation of naturally present lactoperoxidase system in the milk to produce hydrogen peroxide in the bioreactor. The system was designed by immobilizing lactase and glucose oxidase on the nylon pellets using glutaraldehyde coupling with a polyethylamine spacer. Raw milk was introduced into the reactor for 3 minutes and stored at 8 degrees centigrade. The system was found to reduce the natural microflora of raw milk to 0.5 to 2 log cycles. The modification of the system for use in a package will have great impact on milk and milk based industries growth. Limitation for this may be the oxidation of milk compounds by hydroperoxides, which leads to the undesirable sensory attributes of your final product. So, indirect antimicrobial activity is exhibited by modifying the package atmosphere, that is reduced, you are maintaining the reduced oxygen level inside the packaging material by glucose oxidase immobilized with catalase. Few more examples in this category include immobilized enzymes that could reduce the carbon dioxide from the packaging environment. Main concern in this application is the removal of taints, which are otherwise the main indicative of food spoilage, which may allow the consumer to consume contaminated, possibly pathogenic food, leads to health hazard. So, coming to the third category, our third application is your intelligent packaging. The components of intelligent packaging include immobilized enzymes and antibodies. Several indicators are available in the market are time temperature indicators, spoilage indicators and indicators for chemical or other contamination. Although the enzymatic treatment temperature indicator, that is time temperature indicator, that is TTI, are commercially available in the market, do not fall under the NMBP. This area is found to have a suitable methodology for adopting with NMBP technology. Indicators for detecting microbial and toxin contaminations can be manufactured using enzymes or any antibodies. In case of enzyme immobilized indicator, the principle is enzyme catalyzed reactions uses the microbial metabolites or chemical contaminants as a substrate. Specificity of antibody to bacterial metabolites or toxins or contaminating chemical is a basic principle behind the antibody immobilized indicators. So, coming to the summary, food packaging exists to make our life easier. We need packaging to contain foods and protect foods from the outside environment, and also for convenience, and also to communicate the information to the consumers about the food which is inside the package. So, active and intelligent system are a branch of packaging that is truly innovative and offers exciting opportunities for food safety and quality convenience. Non-migratory bioactive packaging is a novel form of active packaging. It is a packaging which elicits a desirable biological response from food system without the active component migrating from packaging into the food. The possible application of this include, as I already told, in packaging enzymatic processing and non-migratory antimicrobial packaging. However, formulation of regulations and stringent implementation of safety aspects of this category of packaging material are need of the hour.